Each week we do something called a community moment. It is an opportunity for a member of our community to get up and in 10 minutes or less talk about something that's interesting to them. Perhaps it's a book they've read, perhaps it's an idea they've been thinking about, or just an experience they've had that they want to share with the rest of the group. If you're interested in doing a community moment, the person you want to talk to is Mike House. He's not here today, so you can talk to me instead if you'd like to get onto the schedule. Today's community moment presenter is a first-time presenter. Her name is Jaime Jensen, and her talk is an impressive title for something that's going to fit in 10 minutes or less. Sizes of Infinity. Here's Jaime.
Hi, everybody. As Eric mentioned, this is my first time doing the community moment talk. My fiance Stephen and I have just been coming here to Oasis for a few months now, so we're still relatively new, and I'm going to talk to you guys about sizes of infinity. Alright, so when we're talking about infinity, a lot of people think, well, infinity is infinity. They're all the same size. They're big, infinitely big. But that's not actually true. Different infinities are different sizes. So when we're talking about sizes of infinity, we need to talk about sets of numbers. So there's the natural numbers. These are our counting numbers, 1, 2, 3, 4, 5, etc. We have the rational numbers that can be written as a fraction. They have a fractional numerator, an integer in the numerator and an integer in the denominator. Then we have our real numbers. That also includes irrational numbers, which are non-repeating infinite decimals like pi. Irrational numbers, the decimal will either terminate, or if it's infinite, it will repeat over and over. And so your irrational numbers are non-repeating infinite decimals. And these are all infinite sets. Your counting numbers go on forever. There's no last number. You can count as high as you want. Rational numbers are also infinite. Real numbers are also infinite. But are they all the same size of infinite? And to answer this question, we're going to talk about a mathematician named Georg Cantor. He was a German mathematician born in 1845, died in 1918. He invented set theory. We've been talking about sets of numbers, so this was really his bread and butter. It's his specialty. And he came up with what's called the diagonal argument to prove uncountable sets. And that's another way to say that some infinities are bigger than others. So let's talk about how you compare sets of numbers. If two sets of numbers are the same size, they can be put into a one-to-one correspondence with each other. When we're talking about a finite set, this makes a lot of sense. Your set only has so many elements in it. So we have one finite set up here, another one down here. To put them into a one-to-one correspondence, we'll just map 1 to 1 element in the set. There's 9 elements in the first set, there's 9 elements in the second set. They're the same size. They both have 9 elements. For an infinite set, we do a similar thing. So in blue, we have the natural numbers again, 1, 2, 3, 4, etc. In red, these are just the even numbers, 2, 4, 6, 8, etc. Now, when you think about this, maybe you'll say, well, the even numbers have to be smaller than all the counting numbers because there's half as many, right? But look what we've done. We have, again, a one-to-one correspondence. We can map every element of the blue into the red. When we generalize the blue set, x, it maps to 2x. So there still is a one-to-one correspondence. These are actually the same size. That's the weird thing about infinity. You can take out elements and they're still the same size in this case. So now we need to talk about Cantor's diagonal argument. So let's imagine an infinite set of decimal numbers where all of the digits are either 0 or 1. So for example, we have 0.0000 forever, 1.11111, 0.010101, and so on. A whole bunch of different arrangements of zeros and ones. And these are a set of real numbers. There's no requirement that these decimals repeat. The only requirement is that each new number in our set is not already listed before. So what we're going to do is we're going to highlight the first digit in the first number, second digit in the second number, the third digit in the third number, and so on, all the way down. And we're going to create a new number. It's going to be the complement of the number that we created with the red digits. So if the red digit is 1, the yellow number has a 0, and vice versa. So we've constructed this yellow number here. Now your new number cannot be in your original list of numbers, just based on the way we constructed it. It differs from our first number in the first digit. It differs from our second number in the second digit, and so on. It differs from every single number in this list in at least one digit. Therefore, it is not in the list of numbers. So, this proves that the real numbers cannot actually be put into a one-to-one correspondence with the natural numbers. They are said to be uncountable. We can't count them with our counting numbers. So they're a bigger size of infinity. They're fundamentally bigger than our natural numbers. Okay, well, we also talked about the rational numbers at the beginning. Are those also bigger than the natural numbers? They certainly look bigger. Our natural numbers, we list them out horizontally, but our rational numbers, the way that we were listing them in a grid, this is an exhaustive list where in the first row, the numerator's all 1 and the denominator increases, 1, 2, 3, 4. Second row, the numerator's 2, then 3. So we're systematically listing all of our rational numbers, and it's expanding in 2 directions, horizontally and vertically. Whereas the natural number list is only expanding in 1 direction, so it looks a lot bigger. However, this image, if you can see it, it's another image of the same thing, listing the grid of the rational numbers. And look at these little arrows. If you serpentine through this grid, then you can actually put the rational numbers into a one-to-one correspondence with the natural numbers. You just have to skip over any number that's equal to something you've already used, like 2 over 2 is the same as 1 over 1. That would cancel out our one-to-one correspondence. So, but still, even so, if we skip over those, we're exhaustively mapping one-to-one. We're exhaustively mapping one-to-one with our little serpentine track between the rational numbers and the natural numbers. So they're not bigger. They're actually the same size as the natural numbers. So the real numbers are bigger, but the rational numbers are not bigger than the natural numbers. And that concludes my talk on the size of the